Hi everyone, welcome to my channel. This is the very first video going up and I have no script for this. I have a vague objective what I want to accomplish. So I'll just jump into it right now, kind of explain who I am, what I'm trying to do, and the way I'm going to go about it. So, as I said, my name is Ben. I'm a data scientist, that's my career. I work for GSK, and one of the main things I do in my spare time, especially over quarantine, less so now, is do Kaggle dataset work. And if you've not heard of Kaggle before, it's a great website. You can see it here. It's simply a website full of datasets that you can use for kind of data science related tasks. They do competitions, they do playground stuff where you just have fun and just mess around and see what you can do. And I was thinking it might be quite valuable as someone who's relatively new to the field. So I've been a data scientist for what now, 3 years. When I was going into the field, it would be really helpful for me to see some kind of live code alongs, to see a really organic data science process of someone seeing a data set, exploring it, seeing what what they can take from it, and then just kind of representing that, as I say, in a very organic way. So this is going to be me attacking this data set basically with no prior interactions with it apart from downloading it. I think I downloaded it a few months ago and just never touched it. So without further ado, I'm just going to jump in. I will be coding in Python. This challenge is a classification, more specifically a binary classification. We're trying to predict whether an individual has heart disease off these 11 or so other variables we can see here. And yeah, I'm just going to jump in. Everything you're going to see me doing is more or less, it's not really a tutorial or anything. It's just kind of demonstrating how my kind of data science approach goes on this data set. I mean, I'm really not sure what I'm trying to achieve here. I'm just going to do some pretty simple stuff, put together some exploratory data analysis, do some model development, keep it super simple, and yeah, just have it recorded, because I think it'll be very useful for me personally to look back on this and see how I think and how I approach problems, and also how I can improve, because I guarantee I'm going to do stuff that's wrong. I really want to give quite a raw view on this, so I will probably say stupid things or do stupid things. But I feel like that's actually representative of a lot of the work that I've done, or a lot of it is trial and error. A lot of it isn't a polished, shiny routine that you see on a lot of videos, especially on YouTube, where people are showing the best side of themselves. I kind of created this channel with the idea to show a very unpolished version of myself, so a bit more of a realistic one, just so you can see what a genuine, raw, organic process looks like. And I promise I won't say raw and organic anymore, so let's just go ahead. So looking at this data set, we can see straight away they've got duplicated observations in it. Interesting. The final data, okay, so they've removed the duplicates. So we've got 918 observations. Cool, that's nice. Okay, cool. So they have like a little thingy here that gives you a breakdown of all the variables. Cool. So we see age here. Nice, nice. And the first thing I'm seeing here is that there are instances of strings inside these columns. So we're gonna have to convert those, and that's an interesting discussion actually. See again here. Yep, I'm going to convert those. Okay. Alright, that's good. Okay, let's see the last two columns. Select all. Okay. Alright, this is good. So this is one thing that does come to mind whenever I see a data set that's to do with classification. The target variable here, always want to make sure that, well, it's not the end of the world if they're not, but it's easier if they are, if they're balanced well. So we've got 410 of the 0 and 508 of the 1. Balanced data set makes it a lot easier for me, because you can artificially like resample them to make sure that they're a bit more equal, which is fine, absolutely fine to do. But it just saves me a bit of effort now that they are well balanced, because if they are imbalanced, machine learning algorithms will typically ignore the minority class. So if this was something like 10 of zeros and this was still 508, you wouldn't get any readings out from any predictions that are made on the 0 class. So that's useful. Okay, I think that's more or less everything we need from this. We know what our variables are. We know kind of what's going to happen next. We're going to have to load the data into our notebook. I'm not sure if I've said I am doing this in Python. We're going to load this into our notebook and have a look and see how we can convert some of these variables so that they're able to be used in a machine learning context. So I've got my Jupyter notebook open here. I like to start off all my notebooks with just a clear heading. Well, that's not a heading even. Wait, can I do it with thingies? Oh, you can, nice. So you can do imports here at the beginning. I'm a big fan of stating all my imports right at the beginning. It really helps if other people are looking at your notebooks. You can see from the outset exactly what what you plan to use, and it stops you from littering them about when and where you need them, which is quite ugly in my opinion. And I mean, functionally it doesn't make a difference, but I think for readability it definitely is. So I don't actually know what I need, so I'm just going to import pandas, read the data in, and work from there. So, cool. Right, okay, there we go. Cool. Alright, so we've got, yep, just the data read in. Cool. Alright, I think next in my mind is I want to check if there are any missing data, so take all the is-nulls and then sum them. Okay, so we've got no missing data, that's great. This also covers NAs if you're wondering. So we're all good, okay, so now next in my mind, to be honest, is go straight into some conversions. I'm going to use label encoding for this. You can use one-hot encoding. There is a difference in terms of label encoding does actually assume relatedness of the individual columns. I'll show a quick example of that. I'm not really trying to do a tutorial, but just kind of explain my thinking. So we have chest pain type here. We want to see all the values that are contained in this this column or this series. So this is a data frame, and every single column in here is a pandas series. So data frames are just collections of series. So if we look at the values held within this specific series here, we can see that it has these 4 types. Okay. And label encoding would basically convert ASY to 0, NAP to 1, ATA to 2, and so on and so forth for however many variable values there are for whichever column we're investigating. And then it does assume a relatedness, so if I import my label encoder really quickly, it will make sense why I'm using it. So just have to call the instance of the label encoder. It's just calling this function from the Scikit-learn preprocessing part of the library, calling an instance of it so we're good to use it, and then we'll have a look at how it actually transforms our data. So if we go chest, that. Cool, and we can see here that I actually don't know why that's the case, why it doesn't just go 0, 1, 2, 3, because it's in the same order, you can see, but they just decided to go for it like that, who knows. But as you can see here, we've now converted these individual counts, these from this column into numeric equivalents, which is excellent because machine learning algorithms will not be able to accept a string value. They don't work well with it. So this way we still maintain the counts for a specific type, but now in like a machine learning readable format. So what we want to do now is essentially transform the rest of these kind of string, I think they're called objects. So if we call df.info here, we can see that these objects here, so sex, mf, so basically we want everything to be an integer, or at least numeric. So we're going to have to convert the rest of these columns that are objects into integers. So how we're going to do that is we're going to make a list of the variables of the columns that we want to target. So we'll put in our transform list is equal to sex is equal to resting ECG exercise angina think that's heart. No, that's chest pains. I think I should really know that. And then we'll have st slope. And then what we need to do is set df transform list, so equal to le.fit transform, and then this is oh, okay, I'm going to be a bit rogue here. Exercise. Oh god, have I spelt this wrong? Potentially. Yeah. Fit transform. Oh no, this is all crumbling. Oh no, well, we're all good. Great, and now we can see that we've passed in everything that we wanted to convert here into this le.fit transform. So all we've done is pass them all in, transform them, and return them to the data frame. So we can see here that we're all numeric now, we're all good, and yeah, perfect. So now that we've got a whole numeric data set, one of the first things I quite like to do is look at the correlations between each one of the variables, and you can do this with a correlation matrix, which is using an inbuilt method in the pandas library. And if you are interested in looking up any of these libraries, by the way, a really great place to look at it is pypi, which is the Python package index, and you can just pass in pandas, and it gives you a really good breakdown of basically everything. So what I'm going to use now is called df.core. Yep, and it just gives you a pairwise correlation. So every single variable within your dataset is going to be computed against each other to work out the correlations with each other. That's about it. And you can see there that they've got a few different correlation methods. And to be fair, I don't know the difference. I think it could be something to do with parametric or not. Not too sure. I probably should know, but I don't. So if we wanted to just call the df.core just on our target variable, so it'd be heart disease, we could do this. Actually, we want to do is sort these values so that they're ascending or descending, sorry. So we set ascending equals false, and we get to see here that we can see every other variable correlated with our target in order. So we can see exercise angina is the most correlated, most highly correlated with heart disease, and st slope is the least. And if you want to look at more general top-line view of how things are correlated in your data set, you can always plot this. So I'll just show you how to do that really quickly. So if we do plt.figure, so this is just to set the bounds of the figure we're going to create. 10 by 6, and we want to set a dots per inch to 500, just so everything's nice and sharp. And then we'll just call sns.heatmap. Actually, I have to import this in, I just forgot. We're going to pass df.core. We're going to pass in cmap, which is a color argument, so it just gives us a nice color gradient. There are others you can look up if you don't like it, and equals true, which basically means for every pairwise correlation we get to see the actual value, with 1 being the highest correlated and -1 being the least correlated. So yeah, as I say, we do need to actually import these in. So for this we're going to use matplotlib, so import matplotlib.pyplot as plt, and then we're going to import seaborn as SNS. This is like kind of, I think seaborn is actually built on top of matplotlib. So these work very well together. In this instance, we're going to use the PLT call to set our bounds and our dots per inch, and then we're actually going to create the visualization using Seaborn. So this is a really good way of using them in tandem to create something quite cool. So if we plot that in, excellent here. So we can actually see, let's make this a bit bigger, a bit wider even. We can see here how everything correlates with each other, and this is, as I say, more generally useful if you're looking for different hypotheses within a data set. You could then further investigate, any other combination of variables. But it is also a nice way, and it looks good on slides, to be honest, if you want to show people general correlation analysis. So definitely worth knowing. Isn't super useful in this scenario. We've got all our information essentially here that we really need for this approach. And yeah. there we go. So the only other visualization I quite like to do, if I'm not looking for a specific, if I'm not looking for anything particularly specific, I like to call pair plots a lot. And a good way to actually see some ideas for visualizations here is to go to the Seaborn gallery. And there might actually be a Seaborn pair plot. So there, yeah, you can see there's lots of information even. And yeah, here we go. So really simple. It plots all of your variables, just almost like the df.core call. It plots all your variables against each other, but it's not looking for correlation. It is simply just comparing, like for like. Sorry. So yeah, I'm going to call something like this. I'm not using this dataset, which looks interesting, but we're going to steal this call again. I mean, I would write these out as functions, but I don't really need to. I'm not going to call them more than once, which is generally the rule of thumb for functions. If you are writing the same code multiple times, you really should write a function for it. I mean, I suppose this would be the only repeat, but I'm just going to copy that over. I'm not too bothered. It's more like a do as I say, not as I do kind of scenario. But so we call sns.pairplot. We have df. And then also what's really useful to do for this is setting a hue, and it's much easier to actually show you what this looks like. So calling this basically means we can see here that in this scenario they've set their df here and they're coloring it by the species in the dataset. And all I'm doing here is something that's relatively the same, except I will be coloring it by whether or not an individual has heart disease or not. And that lets you compare like the normal and the altered the variables quite well. And as you can see here, everything is colored by whether or not an individual has heart disease. And yeah, I think it's pretty cool. It definitely gives you a good idea of where you can go forward if you're looking for some individual visualizations to work with, or at least, as I say, it's just some other hypotheses to work with. I think you can actually call corner equals true, so you don't see the top half, because essentially you're seeing everything twice. So I think you can call this corner argument, and it does at least cut down on some of the screen consumption that this has, which is very big. So let's wait for this to load. Here we go. Yeah, perfect. Yeah, so there you go. It's pretty helpful and definitely very interesting. So yeah, one thing as well, as I said, with the correlation plot, definitely something to know about, something to keep in your back pocket going forward. It's very helpful. And to be honest, I don't really need to do a lot of the visualizations right now. I mean, it's not particularly important for what I'm trying to do here. So I think what I'm going to do is just head straight into just some really simple model development. This is kind of what I would do. I'm not going to do a full process video because it would take too long and I don't have much left on my break. But this is more or less what I'm going to do. So heading. Let's write model development. So we're going to put our imports in. When you're using Scikit-learn, I think you know more or less know exactly what you're going to be using for a classification problem. So you can set your imports out quite early. So what I'm going to do is the following. So from Scikit-learn, so what I'm doing here is calling in standard scalar and min-max scalar. And with these types of like standardization or like normalization methods, there's no real downside to using them. I think the only time where they don't really make a difference is if the algorithm you're using is using gradient descent. That's basically all I know about. So if I actually look up standard scalar, because like I think one thing doing this, just thinking now, is a lot of these concepts I feel quite comfortable with, but when I actually have to explain to other people, it all falls down, so maybe I'm not that confident with them. But yeah, standard scalar removes the mean, scales it to variance, which is quite useful to know. It's as I say, there's no real downside to using it, unless the algorithms you're using aren't using gradient descent. So I think logistic regression, which we're probably going to use, does use it. Wow, I can't bother to read that. Yep. On a convex. Okay, so we do use log regression. So going forward, I think when we're using logistic regression, we'll pass in some scaled data and see how it performs. So apart from that, we need to actually import our train test split in, which is very, very important for machine learning if you're not used to it. So if we have from Scikit-learn model selection, import train test split, we actually import our model in, so from linear model, import logistic regression, so that's just a logistic regression classifier, and then we want to actually import some methods in so that we could evaluate our model once we've completed it and see if we're actually giving us useful results. So from sklearn.metrics, import classification report, and that will do us, I think. Unless let's actually put in another model for comparison. So from sklearn. Actually, no. We'll see what the best one to do. Does random forest? It does, I think. So I don't think it does. So it will make a difference. Anyway, let's just put in random forest because it's quite useful to compare with, which is something I actually do quite a lot when I'm developing models. Is that I'll import in multiple models, compare them, just so we can establish some baseline performance and see if there are any out-of-the-box improvements before we go into some really nitty-gritty optimizations. So let's import that in. So random forest classifier. Cool. Right, we're all good to go. So first of all, what we're going to have to do is set our x and y variables. This common notation is that x is always capitalized. So y is the variable that we're trying to predict. So it's df.heart disease. And then the x variable is the data we're going to train our model on to make a prediction of our y. So we're going to have df.drop, and we're going to drop heart disease from this because we can't train our model on the target that it's trying to predict. That would be a quite obvious example of data leakage. It will do incredibly well, and it won't actually. It just won't work. Well, I mean, it will work too well because essentially it's cheating. So we'll drop those and we'll call our train test split. So train test split is super helpful, is like the backbone of this process here. We're going to be lazy and copy and paste it because I don't want to write it out. And I'll kind of explain what that looks like now. So we have our x and our y, you can see here. You can have our x, we have our y, we have our test size, so the actual proportion of your data set that's going to be used as your test set. We have our random state, which sets more or less the. It's to do with how. What is a random state? It's to do with how you randomly select data for the train test split. I think it's the random shuffling. That's it. It's random shuffling. And to be fair, the number that really doesn't matter. The whole reason it was set to 42 before is because of Douglas Adams, which was the answer to universe, life, and everything is 42. I just did 101 because the instructor I had used 101, and I'm a sheep. So I'm going to pass that in now. And if we actually look at this in a bit more detail, you can see here that our X train is everything except our DF heart disease, and this is going to be a proportion of our data set, so about 2/3 of our data set. So if we actually look at the dimensions of our original data frame, you can see that it's made of 918, and this is 2/3 of it without the column which we've specified to drop. So if we look at our X train dot shape, our Y train dot shape, we can see here that it's just going to be instances of our variable that we're predicting, and we can see that there is two-thirds of the original data set, and then we have our X test, which is going to be the 1/3 of our data set aside, so that the algorithm will look at this data here using the fit from our training set, and then make predictions which will make predictions which can then be compared to our Y test. which is going to be the final subset of our data, which is unseen, unknown, and will be used to measure the performance of our model. So I hope that made some sense. I can appreciate that I am rubbish at teaching, and this is more of like a kind of walkthrough of what I'm thinking. I find sometimes it does help for me to stop and kind of walk through things, just because it comes quite naturally, but we'll have a look. So we've got our data here, and if we wanted to just go ahead and fit our model and then see some results, we could write the following function, which just makes things a bit easier because we're going to be doing comparisons. It's much easier to use a function instead of rewriting this every single time we want to use it. So we're going to call it def model development. And then actually, I was going to put in all the arguments at once, but it's actually more helpful in my opinion to actually go through and write all of the arguments in as and when we need them, so it stops things getting a bit confused, which is often the case when you're writing quite long functions. It does make things easier. 2 secs. So let's go. So first of all, we're going to have to call our model, and we're going to call that, we're going to set model equals, so the algorithm we're passing in, so we're going to call it algorithm. We must then pass an instance of that algorithm so that we can use it. So the first argument will be algorithm. We are then going to fit our model, so we'll do model.fit, and then we have to pass in our x train and y train. Therefore, we're going to have to pass in our x train and y trains, the next two arguments. And we're going to make our prediction, which is ypred equals, and that's going to be our model, once it's being fit on our training data, to predict on our x test data. So, as we've seen before, let's just run this real quick. Our x test is the set of data that is never seen before. It's the 1/3 of our data set that we've set aside. It's going to make a prediction after seeing the training data on unseen data, and then we're going to evaluate it to see how well it's done. So we've got our next variable to add, this argument to add even, and then what we're going to do is you have to call print on classification report, otherwise it comes out all funky. And for that, for our classification report, we have to pass our y true, which is to say the actual values we're comparing with, so that would be our y test. So if we're looking at our y test, then we're going to see this is the unknown. These are the unknowns of the target class that we've set aside. So it's unknown DF heart disease, basically. And then we're going to compare it to our predictions, which we have called ypred. And that will give us a really good idea of how well we're performing. So let's go. So we're going to call our function now, model development. We're going to pass in our algorithm, which is going to be logistic regression. We're going to pass in our x train. We're going to pass in our y train. We're going to pass in our x test, and then we're going to pass in our y test. Sorry, let's just add that in at the end. And then we should be good to go. Missing one positional argument. So x train, oh yeah, sorry. There we go. Cool. So we can see here off the bat we have our classification report measures precision, recall, and F1 score. So our F1 score is essentially just a combination of the precision and recall score. The F1 is also called the harmonic mean. That is, it calculates our mean but puts a really heavy penalty on outlying values, which means that if we're scoring high, it generally means that we've made good predictions. So yeah, we're quite happy with that. Our accuracy is 83, and let's put in some scale data to kind of see how well it goes. So I think if we want to go into a bit more depth on precision and recall, there's a really good article here. I think it's called by ML Mastery, I think it's called, and they go into some really good examples about how you can interpret these values, and it's all to do with true positives, false positives, true negatives, and false negatives. And yeah, I would highly recommend doing it. This is the URL. I would highly recommend you checking it out. All I'm going to really consider myself in this going forward is the F1 score. These are very well balanced, so I'm not going to go into a super amount of detail about it. So let's do some transformations on our training set and make sure that we can't just squeeze a bit more performance out just by scaling our data. So we're going to call standard scalar equals standard scalar, and call an instance of it so we can use it. We're going to call min-max, and here we go, min-max scalar. And then what we're going to do is make some new variables to hold the transform data. So we're going to have ssxtrain and ssxtest, and there's a vital bit you have to pay attention to coming up, so keep your eyes peeled. So we're going to call ss.fitTransform on xtrain. However, you will only do ss.transform on your x test set, and this is to avoid a data leakage. So we're fitting our transformer here on training data, which is fine. The model's, it's allowed to see it, it's okay, it's fine. We can't then fit it on our test data because that will constitute a data leak where the model will be seeing data that it's supposed to be hidden from it and essentially gives it an unfair advantage and introduces a bit of bias into our investigation. So only call transform on xtest, fit transform on xtrain. And then we're going to do xtrain and then xtest equals mm.fit transform. Cool. Right, so if we just want to have a look at how this influences our data, we will have a look and we'll just pass in this ssxtrain here and ssxtest there. And here we go. So you can see that we have actually boosted up our F1 score for both of these classes, so the 0 and the 1 predictions by 0.1 and 0.2, which is, yeah, great. We've squeezed a bit more performance out. We're really happy with that. Looking at it, it's made its main, our main goal here, our main outcome is that it's boosted our precision, which is pretty interesting, and no impact on the recall of 0 at least. It has on 1. That's kind of interesting, and you can kind of go down a bit of a rabbit hole investigating these individual changes. And let's have a look now if model development here is going to make a big difference if it's min-max. You can see mad big improvement there, so as we expected, as before, except it's given us a slightly better performance on classifying our zeros, which is quite interesting, although overall it is the same F1 score. So, going forward you would choose to go min-max. Right, now let's have a look at our random forest model, and it's an ensemble model, which essentially means that it uses multiple machine learning models and passes the input between these kind of like layers of models, which generally means that it performs very well. You get some extra performance out of it. So if you look at ensemble learning, again, something to look at. No, not ensemble meaning, ensemble learning. Yeah, so ensemble methods use multiple algorithms to obtain better predictive performance. So mad mathsy, if you want to have a look at it. There are a few links here, obviously, which are very interesting to go with, and yeah, they generally perform very well. It lets you get some slightly better results in some scenarios, some better results in many scenarios actually, and yeah, let's see how they perform. So if we just want to go try our cookie cutter little thing here, we're going to call our random forest classifier, pass it in, and 0.86, so we've immediately got out the box, got a higher accuracy score, a higher F1 score. It's performing significantly better here compared to our logistic regression. Well, I say significantly, but it's like 0.1, 0.2 higher. In this case here, it's still performing well. If we look here, I don't believe this uses gradient descent, so I'm not sure how it's going to be affected by any scaling data, any scaled data. We'll have a look. This is kind of interesting actually. Oops. As we can see here, it has actually done worse. Yeah, it has actually done a bit worse. So yeah, interesting. That's just kind of a little experiment. I might have a read into that a bit later to see what the deal is. But I think it's all about finding the local. I think when... Yeah, sorry, I'm just having a little think. Okay, so yeah, more or less the same, slightly better on the zero calls. Yeah, so at the moment I think the base base of this is what we'd go with. So our model that we kind of want to use here is the random forest classifier. So if we actually want to see comparisons with the predicted and the actuals, we can do something quite quick here. We just need to create this formula outside of a function. So model, so it's random forest. Okay, there we go. And then if we want to create a data frame called our results equals pd.dataframe, and then we pass it in as a dictionary, which makes it a bit easier. So we put our label in that we want the top of our column to look like, so we'll call it actual. We'll pass in our y test, which is, remember, our unseen data that we're making prediction, that we're going to compare our predictions to, sorry. And then we'll have predicted, which is going to be our y pred. And now we'll have a look. Cool. And now we can actually compare and see, oh, you know, which of these scenarios actually, how they measure up, basically. So if I put measure head and then put in 30, we can see that a lot of it is doing quite well. Yeah, we can see here the actual is 0 and it predicted a 1. And it's interesting to have a look to see how all these things kind of interact with each other. So, and if you wanted to, you could do you could create this to a CSV, which is also quite useful for model submitting predictions. So all you'd have to do is call results.toCSV and do my results.csv. And then if we go back here, you can actually see that we've written it, and you can see here that we've got our index is more or less based on the patient, our actual not predicted, and then you could go ahead and you could send that to your colleagues, or you can use it to submit into competitions, for example, of saying this is what my model thought it would be, and this is what it actually is. So I think that's about it, to be honest. Like, that was obviously a bit of a whistle-stop tour between of how I would approach this problem. This isn't by any means an exhaustive approach that I would take. If this was actually a business scenario, I think what would happen is we would look at our provisional model development, and we would start integrating a few more optimizations in. We'd try different models, we'd try different feature engineering, and we'd see if we can really squeeze the life out of it and get every single drop of performance we can. But just for the sake of this video, this is kind of how I would approach a problem. And if you do want to look into any more of these, I would absolutely encourage it. Kaggle's a great site. Look at some of the things that I've looked up, and yeah, just get your hands dirty with it if you're interested, or drop any comments. Tell me I'm an idiot. I don't care. The whole point of this was really to create a video where you see me being genuine in terms of, this is how I approach problems, these are the stupid mistakes that I make, this is how much trial and error is kind of involved in a data science process. And yeah, I just thought it would be helpful, and if it's not, let me know. If it is, you know, it'd be great to hear. So yeah, leave me a message down below, or don't. Yeah, have a good one.